Hi, everyone. Welcome back. Did you all get to see the museum? Good. Yeah, I know we may have a couple stragglers coming in who are just so captivated by the exhibition that they can't be torn away. But we are moving ahead. So with that, I am happy to introduce our third session on cartographic technologies. And leading us through this conversation is Darin Hayton, who is an associate professor of the history of science at Haverford College. Darin's research focuses on the creation, legitimation, and dissemination of scientific knowledge, especially the science of the stars, namely astrology, astronomy, astromagic, and astrological instruments in pre-modern Europe and later the Byzantine Empire. How, in other words, is science made and made persuasive with an eye to deploying in support of political, religious, and other social and cultural projects? He has recently published a book entitled The Crown and the Cosmos, Astrology and the Politics of Maximilian I. He is currently working on an edition of the medieval Greek version of Claudius Ptolemy's collection of astrological aphorisms. He is also the chair of the editorial board for Lever Press, an innovative open-access scholarly publishing venture intended to celebrate and promote scholarship from, by, and for liberal arts institutions. And Darin will introduce each of our panelists, who will then present their papers.
Thanks so much for that introduction. Thanks to APS for hosting this. This is a lovely event, and I've enjoyed the morning. I look forward to enjoying the afternoon. As commenter, as in person who introduces, I'm going to introduce and then get out of the way. So first, at the far end, we'll hear from Tamara Thornton, who is professor of history at SUNY. She received a bachelor's in history of science from Harvard and a doctorate from Yale in American studies. She has many books, and in the interest of actually hearing her talk today, I won't go through the long list, but if you want, please ask her. I'll just mention the most recent, what looks to be the most recent, which is Nathaniel Bowditch and the Power of Numbers: How a 19th Century Man of Business, Science, and the Sea Changed American Life, which came out from North Carolina Press in 2016. She has an article coming out this spring called Mathematical Geography: The Use of Globes and Race Theory in Early America, and that will appear in April 2020 from William and Mary Quarterly. Next, we have David Spanagel. He's associate professor in the Department of Humanities and Arts at Worcester Polytechnic Institute in Massachusetts. He teaches history of science and history of technology courses there. He's a product of Harvard History of Science program, a PhD there in the mid-1996. And since he wrote this, I can say how old it is. 1996. He's been an active member and officer of the History of Earth Sciences Society over the past 2 decades and currently serves as the History of Earth Sciences Society treasurer. He also has served as a leader in the Forum for the History of Science in America. David's first book, DeWitt Clinton and Amos Eaton, Geology and Power in Early New York, came out from Johns Hopkins in 2014, and more recently in paperback in 2017. And it examined the interplay among science, politics, art, literature, and religious belief at the moment when the newly excavated Erie Canal first brought Americans into direct contact with evidence of deep time. Not to be confused with deep state. It's a different deep. And finally, Penelope Hardy is a historian of science and technology and an assistant professor at the University of Wisconsin-La Crosse. She holds a PhD from Johns Hopkins. Hardy studies the historical intersection of technology and the ocean sciences, and particularly the ways in which technology has historically mediated scientific understandings of the otherwise invisible ocean. Her current book project examines a series of 19th and 20th century research vessels and the cultures and practices surrounding their use in the creation of the field of oceanography. Please help me welcome our 3 speakers and look forward to their papers.
Thank you. It's such a pleasure to be here, and this is the first time that I have delivered a talk where the subject of my talk is at the center of the seal of the institution sponsoring the conference. So my goal here is that by the end of the talk, you will look at that seal differently. And in fact, at least until the 1820s, globes were not just or even primarily spherical maps. Globes are not maps. Now that proposition makes no sense if you're thinking about a globe like this, but it does if you look at early globes. Unlike modern globes, early globes came in pairs, terrestrial and celestial, and that was because the intellectual context for globes was not the descriptive geography of geographical gazetteers and special geographies, but instead something else called mathematical geography, which is really a now archaic discipline that linked geography to astronomy. The two were seen as twins. Now, we wouldn't link them, but you can see here that the two were twin components, the two major branches of a study of the whole cosmos. Mathematical geography considered the Earth as it is influenced by astronomical phenomena. It defined those influences mathematically in a set of imaginary circles, lines, and slices. Now, you're familiar with these if you think, for example, of the tropics of Cancer, the tropics of Capricorn. These are imagined on what was called the terraqueous globe, our planet, and marked on the so-called artificial globe, the papier-mâché version. And these tropics actually define the northernmost and southernmost latitudes at which the sun can be directly overhead at some point in the year. And between them lies the so-called torrid zone. So this is astronomical information on the globe. Globes were the pedagogical tool of choice in the field of mathematical geography. They were used to demonstrate and calculate how observers at different points on Earth experience differing stages of day and night, days and seas of differing durations, and the appearance of celestial bodies at different times. This was the classroom practice known as the use of the globes, and it involved problems on the globes that were key to specific times and places that you solved by physically manipulating the globes. And the functional elements on those globes. So if you're given a globe, you would not get a problem like, where is Philadelphia? That's for a map. Instead, you would be given a problem like, it's 1:30 p.m. in Philadelphia, what time is it in Peking? Or when does the sun rise and set in Baghdad on October 11th? Or where is the sun directly overhead on that date? And here I want to thank Mary Grace Wall and Erin Holmes at the APS for giving me access to one of the Society's 18th century terrestrial globes. I brought along a globes manual, and the three of us worked out how to do at least one problem on it. And I can assure you that for people born in the 20th century, this is not at all obvious. So again, unlike maps, early globes were, for the most part, produced by craftsmen specializing in precision instruments. In America, and take a look at what flanks the globe on the seal of the APS. In America, these expensive London imports, because Americans didn't make them until 1810, were sold alongside precision goods. And unlike increasingly ubiquitous maps, they were used by just three select niche audiences. There was the learned audience. Every colonial college used globes, pairs of globes, to teach astronomy and mathematical geography. College-bound students, here the grammar scholars referred to, needed to have studied the globes to get into college. And gentlemen with interests in natural philosophy, like Thomas Jefferson, owned them. You can see his globe there, which he ordered from London from the firm who whose catalog of optical, philosophical, and mathematical instruments he had picked up years before. So this is the learned audience. There was also a genteel audience, young men and women with pretensions to gentility, who would go to academies where they would learn the use of the globes. Again, here I have an advertisement for a female academy. Boys were learning this as well. But some of you may recognize this as the image on the cover of Mary Kelly's book. But here are young women studying the use of the globe. So the genteel audience. And finally, the use of the globes was one of those mathematical subjects that figured into the curricula of vocational courses, targeting those in commerce and navigation. So globes are not just maps. But since you're map people, I'll acknowledge a few points. First, yes, globe makers and buyers valued the latest in cartographic information. And second, there is a gray area here because globe literacy seems to have influenced map design, and I need to think a lot more about this. So here is Charles Barrell's The World Enlarged from the Encyclopedia and Adams's Globe. Executed in what we term, or what was termed, the globular projection. And the real sign that this is globe-derived is this wavy ecliptic line, which you will find on a globe, which marks the apparent route, annual route of the sun. Here's another example of globular projection, and in fact, the Mercator and globular projection seem to have jockeyed for position, and there were advocates and arguments for each during the 18th and 19th century. So I've just opened the door on this. I have no idea what's on the other side. But back to the use of the globes. I approach globes first as artifacts in a consumer-sensitive marketplace, and second, as material embodiments of a particular understanding of the cosmos. I've already talked a bit about the first, and here I can only offer a few thoughts about the second, suggesting their distinctive cognitive and cultural possibilities. I'm not arguing that globes determined how people thought, but nor did they merely reflect ideas. Instead, they offered users distinctive perspectives based first in their materiality, their hands-on, their three-dimensional, and so on, and second in the idea of mathematically homogeneous space universally governed by natural law that they embodied. So globes opened up a range of possibilities for imagining far-flung places and peoples, as well as the human place in the cosmos. In other words, they shaped global thinking. I'm focusing on two broad questions. This is obviously part of a larger project that I'm working on. First, what distinctive modes of imagining other places and peoples did globes offer, and what were the resulting implications for thinking about and engaging with distant locales? Like Eurocentric maps, terrestrial globes could reinforce a narrative of Western dominance. Their functional elements, for example, divide the Earth into 4 equal segments, suggesting objective equivalence even as they obscure the lower hemisphere visually. But there were other possibilities. If, for example, every point on the globe is mathematically equal, and that was actually lesson number 1 in globes manuals, so too perhaps are all people, at least as they are all subject to universal natural laws that govern the entire cosmos. Of course, under those same universal laws, the Earth's axial tilt does create some differences, and that was actually the starting point for the latitudinal theory of skin color. In language suffused with mathematical geographical terms, including explicit reference to globes, thinkers steeped in these studies argue that complexion correlates with solar exposure, and therefore shifts in quantitatively precise gradations from the equator to the pole. A man like Princeton's Samuel Stanhope Smith, who actually taught geography and the use of the globes to George Washington's step-grandson, Smith forwarded this theory just to provide a scientific footing for the unity of humankind, but abolitionists like Thomas Clarkson used it to decouple blackness from inferiority. Again, globes don't tell you what to think, but they do give you ideas. One more example of these ideas are the notions suggested by working problems on the globes. Take what I call scenarios of simultaneity, like this one in Jedediah Morse's Universal Geography. It calls on you to imagine not just other places, but other people, breakfasting, dancing, going about their business just as you do, and simultaneously with you. That recalls Benedict Anderson's argument that a sense of temporal coincidence, an awareness of and belief in the steady, anonymous, simultaneous activity of others, that these were key to the formation of an imagined national community. And he singled out the newspaper and the novel as 18th century devices for the presentation of simultaneity. I would suggest that we might think about adding the globe as shaping a sense of global community. And perhaps, and this is more speculative, given the hands-on experiences that they called for, globes could have provided an especially visceral sense of connection, even humanitarian sympathy with distant peoples. A second line of questioning is this: what did globes suggest about humanity's relationship to the cosmos, and how did such notions relate to contemporary science and theology? Celestial globes had long featured the constellation creatures of the animated folk cosmos, but increasingly they delineated scientifically notated star clusters, lodging the Earth within the vast grid of rationalized space. But simultaneously, globes sustained older ways of imagining space. Terrestrial globes featured zodiac signs on their horizon rings, for example. And though there was no doubt as to the truth of the Copernican system, well into the 19th century, globes modeled a geocentric system. That's right, they're Ptolemaic. I mean, everything is funky about these things. You spin them, not west to east, but east to west. It's counterfactual, not just counterintuitive. Ultimately, globes were artifacts of a cognitive universe in which the import of celestial bodies lay in their relationship to individual human experience. There are a lot of dissonances here. Astrology on the one hand, Enlightenment celestial mechanics, a smallish, closed, human-centered cosmos, and a vast universe in which the Earth is lodged somewhere seemingly randomly. So if we're going to ask questions about the disenchantment of nature, the rationalization of cartographic space, we need to see what globes had to say about all of this. And I'll just end very quickly with a few images of the after picture, after the 1820s, certainly picking up steam in the 1850s. This is essentially a modern globe, right? It's all map, no calculating elements. But computational globes didn't disappear completely. Here you can see in this catalog of 1878, you can get computational globes, you can get non-computational globes. And this 1885 catalog clarifies the shift, right? If you never desire to work problems, get this kind. So who's learning this archaic skill at this point? Well, I'm still looking into that, but here's one sure sign that the use of the globes had become of no use at all, because one of the major categories of people still learning the globes are girls. So thank you.
So my strategy today, hopefully some of you read the paper, and I will touch upon it, but I'm going to attempt to introduce a little more of the origins of the situation that generates that scenario I explore in the paper, and explore some of its implications for politics, diplomacy, and theory in the proximal time envelope that I talk about, 18 teens to 1830s or 1840. Great. So from this image, we can see how exceptional the Canada-US border is, not only for its lack of fortifications, but even its instances of local agreements to share water resources. This is an interesting border for a lot of reasons. As my pre-circulated paper suggests, the Enlightenment elevated science to prominence as a provider of practical means to address a vast array of challenges facing modern society. Champions of rationality promised technical solutions for situations where natural obstacles or hostile environments required the application of ingenuity to ensure human survival and cultural prosperity. What seems more surprising today is the contemporary hope that some ambitious savants cherished that the natural sciences could also help to resolve troublesome and complex social and political problems which plagued Europe's emerging nation-states during the 18th century. One such problem was the question of how to reduce or even eliminate the need for nations to engage in needlessly destructive warfare over disputed territories. The Treaty of Ghent delegations, pictured here, faced a challenging task of designing a peace that could resolve chronic tensions between the United States and British Canada and settle a boundary that had seen frequent armed incursions over the preceding half-century. These diplomats included, for Britain's Regency government, the Admiral Gambier, Henry Goulburn, a parliamentarian undersecretary for war in the colonies, and William Adams, a doctor of civil law. These aren't names that are household names for any of us, I don't think. The American negotiators included prominent politicians like Henry Clay, but also intellects such as the future President John Quincy Adams, the Princeton-educated Federalist former Delaware Senator James Bayard, and the man we heard about this morning at some length, the Swiss-born Jeffersonian mastermind of internal improvements and former Secretary of the Treasury, Albert Gallatin. Initially, Britain's representatives were instructed to be very forceful, demanding, as the questioner in our last session this morning noted, the establishment of a buffer state for the Native Americans in the Great Lakes region, which would have been composed of parts of the state of Ohio and the Michigan Territory. News of battlefield victories for each side, however, took months to cross the ocean. So the diplomats finally settled on a curious solution to their own lag time predicament. Although Americans had cherished conquest of Canadian territory at the outset of the War of 1812, the worsening economic and trade situation induced Washington to instruct its diplomats to accept a status quo antebellum in terms of the boundary. Rather than the legacy of military field victories, whose outcomes were never quite certain across the ocean, diplomacy informed by science would be entrusted to negotiate any alteration of those previous boundaries. Treaty of Ghent articles authorized a series of joint international boundary commissions to be formed over the coming decade to examine and redefine each portion of the boundary from the Atlantic Ocean to the Lake of the Woods. We might well wonder, in this detail of the upper left-hand corner of the Mitchell map that people have talked about at several points today, why were scientists included on those commissions? Treaty of Paris language from 1783, west of the Great Lakes, contradicted physical possibility. Based on Mitchell's 1755 map, the diplomats who met in Paris to negotiate an end to the revolution had supposed the source of the Mississippi River to lie somewhere north and west of the Lake of the Woods. White explorers would not reach the fabled source of the headwaters of this interior waterway until native tribesmen finally escorted Henry Schoolcraft to the place he dubbed Lake Itasca, a cleverly abbreviated truncation of the Latin for true head, veritas caput, in 1832. Decades before that long-awaited discovery, however, rumors that the Mississippi River began well to the south of the supposed latitude referent had induced diplomats who negotiated the Jay Treaty in 1794 to recommend the matter of the western extension of the Canadian border to a process of arbitration. As you've seen from reading my paper, the demilitarization of the Great Lakes after the War of 1812 was accompanied by a remarkably comprehensive hydrographic and geological investigation of the region. Dr. John Bigsby, a naturalist who belonged to the British Army's medical staff stationed in Canada, served as Assistant Secretary for the Boundary Commission. Major James Delafield, an amateur mineralogist, served in a comparable capacity for the Americans. Bigsby's extensive journeys to document the terrain and physical geography of the Great Lakes and his work on the thorny problems of determining what is the middle of a large lake and identifying the main channel of water as it flows around assemblages of islands. By doing this survey work, Bigsby and Delafield also uncovered geological evidence of widely scattered massive boulders, beds of sand and gravel, and other curious landscape features which we now attribute to repeated episodes of continental glaciation. In the spirit of international scientific cooperation, Bigsby's findings were publicized both among British colleagues and in the American Journal of Science that came out of New Haven. The boundary determination work certainly presented earth scientists like Bigsby and Delafield a rich opportunity. Characteristic of popular contemporary theories of catastrophic flooding, no geologists anywhere had yet conceived of an ice age theory yet. As you can see from the passage quoted on the slide, Bigsby inferred from his observations evidence of a tumultuously violent geological past. English geologist John Finch, and here's the surprise for our poor commentator, who also happened to be chemist Joseph Priestley's grandson, attempted to translate Bigsby's achievement into a rational theory of boundary design, which he promoted in an appendix to his popular 1833 Book of Travels of the United States and Canada. Finch noted that small streams form better boundaries than do large rivers, that oceans provide the most enviable borderlines, but he allowed that large lakes and mountain ranges may serve almost as well to effectively keep peace between nations that respect those barriers. He concluded that the North American lakes do form a good natural boundary between the United States and Canada. Alternatively, of course, Thomas Jefferson's idealized mode of inscribing rectangular grid of latitude and longitude lines across the continent was already designating the bounds of townships throughout the Trans-Appalachian West. This more abstract mathematical, astronomical technique for territorial boundary definition would certainly be widely utilized in the decades to come, both in reifying the 49th parallel to separate Canada and the US across the remainder of North America, and as I look forward to studying more in the book project, various European colonial schemes for carving up Africa and the Middle East later in the 19th century. Finch would not have approved of this application of science to diplomacy. I quote, "The most clear, the best defined, the most regular parallelogrammatical empire ever made by the hand of a skillful mathematician is not so likely to retain its boundary entire as an empire with irregular but strongly marked limits formed by the rude hand of nature," end quote. Finch continued, "For all these reasons, in making future treaties of peace or in fixing the boundaries of those semi-sovereign states called into existence by the fiat of the American Congress, not the mathematician, but the geographer, or the individual who has the greatest knowledge of the country in dispute, should be consulted." Peaceful settlement of the Maine-New Brunswick-Quebec boundary question would elude both negotiators and scientific investigators for several more decades, precisely because the 1783 Treaty of Paris had designated a, quote, line of highlands, which could not actually be found on the ground. In Derek O'Leary's paper this morning, we saw this map with a green line hugging what appeared to be a chain of prominent mountaintops hugging the southern edge of the valley of the St. Lawrence River. Those mountains aren't there. So it was very frustrating for geographers and geologists who got involved. This particular boundary dispute bumped up to high-profile international mediation. In 1827, President Adams, John Quincy Adams, appealed to the good offices of King William I of the Netherlands to review the competing claims and offer a compromise. Setting aside the deadlocked scientific question about where these highlands were, the Dutch ruler offered an arbitrary division of the disputed acres, but local political leaders in Maine and Massachusetts were so vocally hostile that Andrew Jackson had to scuttle a compromise that he privately considered to be reasonable and attractive. Let me end by summing up. The demilitarized Great Lakes region did reward the innovative gamble that the Ghent Treaty diplomats had placed in it in 1814. They ask scientifically informed boundary commission teams to explore and jointly agree upon where to draw line segments upon a new map crossing the eastern half of the North American continent. Invasion attempts did diminish to zero. Although nobody clearly anticipated what depth and breadth of natural knowledge expertise was required, contingencies in the choice of participants and in the political decisions made on the ground enabled what I'm going to consider a misleadingly positive test result. Thank you.
I'm glad to be included here, even though my paper is mostly a little later and a little less American than many of these. And I will also assume that many of you have read it, but I'll try to tell the story while also letting people who have read it see a little more of the visuals involved. One thing about history of technology and history of cartography is they're so very visual. It helps to be able to see the things we're talking about. So I'm looking at scientists in the, and I'm using the term anachronistically, of course, in the 19th century, who are starting to investigate the ocean as a place that science can understand, and particularly are trying to figure out what the bottom of the ocean looks like, and then putting that new knowledge to scientific use. The first person to do this is an American naval officer named Matthew Fontaine Maury. He becomes superintendent of the Depot of Charts and Instruments for the U.S. Navy in 1842. And he starts making efforts to make good charts, not just sort of traditionally navigational charts, but also including information like winds and currents and other sort of meteorological conditions. He's ostensibly helping the merchant marine, so Congress will grant him the use of some ships to send out to sort of check the routes that he's finding that'll be safer for merchant vessels. But he sends them out into the Atlantic doing what really looks to the modern eye like oceanographic work. They're zigzagging across particular courses, and one of the things they're doing is sounding. Trying to get the depth, but also take samples from the bottom of the ocean. Of course, sailors have always sounded, checked the depth by tying a weight on the end of a line. But he and his officers, including Lieutenant John M. Brooke, develop new technologies for sounding so they can try to take samples even from the very depths of the Atlantic. So this is a weighted sounder that Lieutenant Brooke developed. That would sort of be the prototype that all the others afterwards would be based on. But it takes a tube and has a weight on it that will drive that tube into the bottom, and then the weight detaches, and then a little valve shuts, capturing a sample of bottom sediment that you can then pull back to the surface. The naval officers, of course, will use the sounding information to tell them the sort of hydrographic things naval officers have always wanted to know about. Usually they've worried about near the coasts. You're most concerned about how deep it is if it's a place where you might be in danger of running into something. But Maury will start using this to make maps even of the middle of the Atlantic. So he publishes this bathymetric chart, the first bathymetric chart of the Atlantic Basin in 1853. And he will continue, this is a bold chart to make when he only has a few dozen numbers from the entire area. So it's perhaps not much like a chart of the Atlantic would look today. But he will continue revising that. He recognizes that this is preliminary data, and he will continue revising this and publishing new versions over the next 8 years until 1861, when his U.S. naval career ends at the start of the American Civil War, because he's a Virginian and chooses to leave and go join the Confederacy, where he will have a very lackluster career with the Confederate Navy. But this chart will make the rounds. He publishes it with his sailing directions to go with his wind and current charts. And the samples he brings up will also be important. He sends some of them up to a microscopist working at West Point, who will examine them under a microscope and discover that the sediment on the bottom of the Atlantic is actually made up of lots of tiny little shells. And then that will start a scientific debate over, do these tiny little creatures, this is the remains of these creatures, so did they live and die at the bottom, or did they live somewhere in the water column, and then when they died, sort of their remains snow down onto the bottom to blanket it? So this is going on in the US, and of course there's a conversation between the US and other parts of the world around science. In Britain, efforts to study marine biology are led by people like Edward Forbes, who started out at the University of Edinburgh. And a sort of culture of studying nearshore marine biology really rises at the University of Edinburgh. And he's popularizing dredging, which is using these sort of nets with an iron bar to hold it open that you would lower to the bottom and sort of drag along the bottom to catch things, and then pull it up and see what you've got. He's, of course, exaggerating a little bit when he draws this picture of these guys using this massive net from this tiny rowboat, but they really were dredging from rowboats, fishing boats, eventually yachts, if they were either lucky enough to have one or had a friend that they could hook up with. And here, of course, he's sort of making fun of it. It's every fisherman's assumption that this is what's going on, right? Surely the fish are down there. They're just laughing at me rather than getting in my net. But he is mostly interested in the zoology, but he's in conversation with geology at the time. Forbes would die in 1845, but others from Edinburgh and elsewhere would take up the mantle here, including Charles Wyville Thomson. He was another British naturalist, and he heard about some Swedish work where they had retrieved samples from the then extreme depth of 300 meters. And they found a crinoid, a little creature that had previously only been known from fossils. This was very interesting in the wake of Charles Darwin's work, because Darwin had predicted that you would find there was less evolutionary pressure at the bottom of the ocean, so you would find these sort of living fossils down there. But he recognized the reason that the Scandinavians are able to do this is because one of them works for government fisheries and has access to big government ships. So he teams up with another British naturalist to convince the Royal Society and Royal Navy to sponsor some cruises to try sounding in relatively deep water. During these preliminary cruises, they modify the dredge. They discover that when you're on rocky ground, the dredge can't pick much up. The ship's captain suggests what the scientists call hempen tangles. The sailors call them swabs, that they just attach to the dredge and stuff will get caught in that they can pull up as well. They also used variations on Brooks sounders, which sort of continues to develop over the years. These summer cruises went so well that Thomson and Company then asked the Royal Navy and Royal Society to sponsor a longer cruise. And this is the scientific circumnavigation of HMS Challenger. It goes around the world from 1872 to 1876. And it's really the first expedition whose principal purpose is to study the ocean itself, not just to sort of look at the ocean a little on its way to the place it really wants to see. This is a naval vessel with a naval crew, but they embark 7 naturalists, including Thomson. And of course, here's Thomson. The gentleman next to him is navigating sub-lieutenant Herbert Swire, which if you read my paper, Swire publishes his memoirs of the trip later, and a couple months in, he writes in his journal that all we seem to do is dredge, and all we ever get with the dredge is mud. I hope it means something more to the naturalists than it means to me. The naval crew was important because they did all the actual work, both the manual labor of hauling these lines and dumping them, and of course then having to clean up after dumping all this mud on the deck. But also the naval officers did their traditional hydrography. So they are navigating and they are sounding, and they're going to really be important to the naturalists because that's how the naturalists can make claims about the samples they get coming from very specific areas. So these are the kinds of things they're bringing up. They're bringing up the same sort of tiny little creatures that they had found, the Maury's people had found in the Atlantic. And they find, they use these, they have an onboard laboratory, I'll show you in a second, but they're able to use these to sort of get themselves into conversations on geology that are happening in Europe and America at the time, because these tiny creatures are actually the same as the ones making up the Cretaceous chalk layer in Europe, such as at the White Cliffs of Dover. They're aided by the fact that they have this, both a physical and a chemical laboratory on board that allows them to analyze results as they go, rather than having to sort of send them back to shore and wait to hear things. So over the 3.5 years of their trip, these naturalists and naval officers working together made maps of the bottom. As they got into they expected to find those little Globigerina ooze critters everywhere. As they got into deep water, they found out there were different kinds of critters, different kinds of oozes, as they called them. So they were able to make maps of what the bottom was made of. And they turn it in thus they turn this into a known space. This place that they could never see, that they could never actually touch, becomes a place that they are claiming as an appropriate realm to do science, and about which they can make claims and even illustrate and make it into this really colorful landscape. And with it, they are making arguments about ancient and ongoing geological processes on the Earth that lets them participate in scientific conversations going on in America and Europe at the time. Thank you.
Okay, thank you very much for 3 really, really interesting papers that take us into very specific, I think, very specific moments of the 19th century and cartography, maps, very broadly understood. I'm a bit of an interloper here, I will confess. So I'm going to highlight some things that jumped out at me and that are interesting to me. And because I didn't provide a paper, I am lucky enough to be unmoored from having to say anything concrete, but I can say something provocative that is completely indefensible, but perhaps we'll start some sort of conversation. But first I want to say, with Tamara's paper, what we get is this great sort of opportunity to come into, shall we say, a pedagogical space, classroom space, and understand how maps, globes transform, but globes are related to maps, but globes are instruments. Maps might also be instruments in this space. It'd be interesting to think about how they're interacting. But seeing globes in this context as functional and having a function beyond what we tend to think of as maps showing relationships, spatial relationships between places, and globes invoking or continuing this tradition of mathematical geometry and the sort of Ptolemaic system. David takes us out of the classroom space and takes us into the frontier, and we get to traipse along in the muddy, wet hinterlands of North America, west of the Great Lakes. And we watch people of the Joint Boundary Commission that get sent out by the Joint Boundary Commission try to negotiate this space, and negotiate the space for people who will never be there, people who have a vested interest, but have to depend on these sort of proxies, and the way that those people, the proxies, the people who are wandering through the wilderness, are also doing something. They're doing something concrete. They are using instruments. They're taking measurements. And again, connecting this in I think, important ways, at least in my mind, to issues of instruments, mathematics, astronomy. With Penelope's paper, we see, again, cartography as the product of, in many ways, the product of very specific scientific inquiry. In this case, sounding, people going off and invoking certain sciences. And cartography, in this instance, becomes almost a byproduct. They're doing something, and they produce maps. They're dredging. They're bringing up mud. Lots of mud. But once again, we see, shall we say, in the field, although in this case it's on the sea, negotiations occurring between the people who have been sent out and the people back at home who have a vested interest in this. So these three papers, for me, again, fascinating. They raise questions, however, and I'm going to just sort of wander quickly through a couple of questions that come to mind for each of them. With Tamara's paper, I think, okay, there's a tension in our mind between a Ptolemaic system that had been jettisoned by the 19th century and a Copernican system. But I dare to say we're all Ptolemaic. How many people today said, oh, the Earth rotated so that we could see the sun again? No, we said the sun came up. I'm not sure there's quite such a tension. Moreover, the tension between a Ptolemaic system as represented in a globe and the Copernican system that we might accept, it had long, if that's a tension, that had long been there. Star maps from the 16th century, pre and post Copernican revolution, had depicted star charts in that way. So had globes. There wasn't a big concern when the Copernican system became dominant in the 17th century. I'm also interested in other pedagogical instruments that would be inherently Ptolemaic, but also used to teach astronomy at the time. And here I'm going to, if any of you know me, I'm going to say astrolabes, because that's what I always say. Astrolabes are, for those of you who don't have a handy astrolabe, astrolabes are planispheric. They're a projection of the sphere of the heavens onto a flat surface so that you can do things with them. Astrolabes were still commonly used as pedagogical devices well into the late 19th century throughout the world as ways of teaching kids about how to do just what you were talking about with globes, how to tell what time it is, where's the sun, this type of thing. So I'm thinking about how are globes related to other pedagogical instruments. For David's paper, I keep thinking, okay, boundaries, but this sort of sending people out to do this work and negotiating the land has been around for a long time. And I'm going to gesture to Emperor Maximilian I, who sent a pair of humanists and an astronomer/astrologer out to map Hungary. He wasn't really interested in Hungary per se, but he was interested in where the boundary between Hungary and the Holy Roman Empire, Austria in this case, lay. And he was because they were constantly fighting over it. It seemed to work with respect to the Hungarians. Unfortunately, the Turks showed up in a little while, and that screwed everything up. But at least with respect to the Hungarians, that project seemed to work. And then I wonder, David makes a mention of how these maps that produce this boundary constrain the motions of native peoples. And I wonder, how much can maps constrain movement, for people who don't recognize those maps, for people who don't use those maps? In what sense is it constraining motion? For Penelope's paper, I'm really intrigued with the way that technologies in the field are at play here. And here I'm thinking about the way that knowledge is made by virtue of a person's sort of status. Penelope talks about how these dredges were, shall I say, improved by the captain's suggestions. Well, in the 17th century, that would have been an odd thing for the naturalist to rely unproblematically on a captain or rely on the handiwork and labor of the sailors. So I'm really intrigued as to how that happens. So what links these three? Well, I think a lot of things link these three papers. The one is they foreground for us the way that the science of spatial representation, I don't know, cartography, maps, I don't know what we want to call it, is intimately dependent on a whole raft of other sciences. We've seen astronomy and geography here. Particularly with Tamara's paper, we're reminded that maps, globes in her case, they're functional. They're doing something important, and not in that abstract political way, but sometimes they have clear functions. All three of these papers also, for me, raise the question of what is it that is being represented and how? As I was sitting here, and I'm paying attention to time, so I'm going to be quick here. As I was sitting here in the morning, I kept seeing echoes and words that I've heard thrown out a lot: accuracy, representation, reality. And I wonder, in what way do we mean those? In what way are maps representational? In what way are they representing reality? In what way are they accurate? And I'm going to close by invoking the long-dead spirit of R.G. Collingwood, who said, we risk misunderstanding an artifact from the past when we bring our own questions to bear. when we try to understand that artifact as answering a question that somebody in the past had, then we might begin to understand it. So if we rephrase the terms accuracy, representation, and reality, maybe even get rid of them entirely, what might we find in these maps and these globes? Thanks. Do you want me to point to questions, or you? Yeah, okay.
Anybody wants to respond to Darin's remarks, and then we'll take questions.
I've got one point. The second question you gave me about how does the map constrain motion of native peoples. In the paper, although I didn't discuss it here out loud, I talk about the circumstances by which this boundary commission decides to award an island on which the British have had a fort. And this island goes to the Americans when the main channel goes on the other side of the island, according to the hydrography. And that's a major concession, and the British dutifully fold up their fort and go home. Now, as you recall, in the War of 1812, in the Great Lakes, a number of Indian tribes were allies of the British, and they considered themselves, if they had to, subjects of His Majesty rather than residents of some piece of the United States. And Indians were in the habit of transgressing the boundary all the time. But now when the fort is gone, they actually don't have a place to which they can go and sort of appeal to His Majesty for supplies and trade goods. And so they really, either they have to relocate or traipse a great distance now to be able to maintain that affiliation. And so that's a kind of a good concrete example.
Thanks.
I would like to just, I'm glad that the questions of that partnership and the, sort of what's being represented came up, because those are, in fact, yes, those are the super interesting things happening here. The partnership is pretty new, but a lot of it's because of the need to access deep water and the recognition that who can access deep water? Well, it's the Navy. And so they sort of have to forge this partnership, and the Navy's getting and the government are getting stuff out of it too, because they're using a lot of the things the scientists tell them about the bottom to then decide, well, can we put a telegraph cable here, or these kinds of questions that are interesting to governments. But it's hand in hand with that question of representation, because from a scientific viewpoint, the question is about authority, right? How can we make authoritative claims? And so part of what especially if you're a naturalist working in a laboratory gives you some claim to authority, but here you are in what's supposed to be a controlled environment on board a ship, which is very not a controlled environment. And so the sort of accuracy of navigation and hydrography that you can count on naval discipline kind of instilling gives them some claim to authority, and so they can sort of match that with, make claims that actually the ship is a better place to do science because of that discipline, because of the place it's happening, because in order to do good science in a laboratory that's moving around, you have to be really good. And so this somehow proves that they are in fact doing better science. So it is interesting how they're trying to negotiate that. What are we representing, and what kind of authority do we have to make these claims in that environment?
Okay, I'll jump in.
None of you get to jump in, sorry.
Yeah, the Ptolemaic versus Copernican. All of the Globe's manuals acknowledged this kind of dissonance, but they didn't seem all that disturbed by it either. So they would say, well, of course, this is only the apparent route of the sun. Of course, we know the sun doesn't actually move, and so on. So there isn't any great disturbance about it. There is a globe manufacturer, maker in late 18th century who tries to invent Copernican globes and does. They just don't take off. Nobody's interested. And that's because of the last point you make, which is, that's a real gem. What is the real question? That it's like Jeopardy, right? Here's the answer. The globe is the answer. What is the question? So when we look at globes, we might say, well, surely the question is, what is the nature of the cosmos? That's not the question. And they would tell you, you want to know the nature of the cosmos? Get an orrery. Get a planisphere. You want a model of reality? Get that. The real question are the questions in the Globe's manuals, which all have to do with individual human experience. You are in Philadelphia at 2:30. What is your experience of astronomical phenomena? These are not questions that drive us today. You know, the kinds of questions that you find in the Globe's manuals, who cares, right? We want to understand the system of the world, but we don't actually feel driven to answer dozens and dozens and dozens of these questions about time and place specific experience of the cosmos. That seemed to have been important through the 1810s, 1820s. Then they cease to be important, which leads to a whole other set of questions.
I wonder if the panel would address the subject of great circle routes and the role that the globe played in our understanding that that was probably a much shorter way to get from A to B than simply looking at a planisphere or some other flat representation.
I can't really speak to the role of the globe. It would obviously make sense. Matthew Fontaine Maury is certainly pushing the Great Circle route as in his efforts to help merchants sailing faster routes. He is suggesting this is the best way to go. I don't have anything about his sort of technique for arriving at that, and I doubt he was the first one to think it up or anything. I don't know when that started. But he is certainly advertising this is how you should navigate, is along these routes that will be much quicker.
Well, certainly, at least in America, through most of the 18th century, most mariners are, they're hugging the Atlantic for the most part. At the most, they're going across the Atlantic using dead reckoning, whatever. It's really only when Americans begin to engage in global trade. And Europeans, of course, are engaged in this much before. So when you do global trade, then you need to think spherically, quite literally. You need to do spherical trigonometry. You move up a step, and you're the mathematician here, I'm not, but you move up a step in the level of mathematical skill that you need. You need to think three-dimensionally. You need to think in terms of the globe. So, which is one reason why globes are involved in navigation education, not in actual navigating, but in navigation education, so that you can work in 3 dimensions. So those who travel the globe need to think in 3 dimensions. Globes are part of the education for doing that.
This has nothing to do with my paper in the background, but navigating across oceans is not like flying great circle routes either. It's about understanding the prevailing currents and prevailing wind systems, and that's what Maury's first task is when he gets all these captain's logs, which are a total mess. He wants to create the map of prevailing, typical, at different times of year, typical wind patterns, because that's really, for sailing ships, going to determine the speed, not the number of knots you cover, distance.
Yeah, and as you say, he sort of, when he takes over the job, inherits all these old logs and starts, he had been sailing master on a ship and asked people, well, what's the best route? And they were like, I don't know, you just kind of go. And so he was really upset that this wind information wasn't available, so that's what sets him on this project. But he supposedly also taught himself spherical trigonometry by drawing on cannonballs, so clearly there was this spherical thinking. They wanted to, and he in particular was upset that the way midshipmen were taught to navigate was very rote memorization of sort of how to do it, rather than being taught the theory. So he tried to popularize, no, here's what you're really doing when you do that method. So.
How about Nicholas? The only name I know in the audience.
Thanks.
We'll head that way.
Hey, Tamara, I have 2 questions for you, and I just want to say I enjoyed all of your papers immensely. So one, I'm kind of curious, do 18th century debates over the shape of the Earth, whether there's a bulge, where it is, if it's along the poles, if it's along the equator, is that something that globe makers or globe users are engaging with at all? Is it something they're interested in? And then my second question, hopefully that's just a quick answer, but my Second question is kind of about the symbolic role of globes, if that's something you've thought about, especially in paintings. And I'm thinking about, from the 16th century, from Elizabeth's Armada portrait to in this exhibition, the portrait with Washington. And everybody's kind of engaging with the map except this one kid is off with a globe. So I'm just curious if you're seeing kind of a change in this period about what that symbolic role is.
Right, okay, so on the shape of the Earth, in the preliminary matter in these manuals, they go through, various astronomical and geographical issues, and they do discuss the shape of the Earth, and then they put that aside. They explain when you're talking about the artificial globe, it doesn't matter. We can think of it as a sphere, so that's bracketed. In terms of the symbolic use of globes, yeah, it's dominion, right? I can't remember which mission to China it is. Sometime in the 18th century, a British commissioner goes with a bunch of stuff to present to the emperor. One of the things are a pair of globes. As you say in portraits, it's about dominion. Even when you look at mercantile portraits, often the way they are placed with their globes is, this is mine. They've got their hands on it. They may be pointing to particular places. The same thing with military figures. They may be pointing to the part of France they just conquered, that sort of thing. So absolutely, it's about dominion. But I think that's what a lot of the scholarship has focused on, because I think a lot of the scholarship on maps has focused on the relationship between maps and power, which makes a whole lot of sense. There is that aspect to globes, but there's another story to be told as well.
What do you think that story is, like from a symbolic? I mean, if they're just doing exactly the same things as maps and portraits, or do you see that they're doing something potentially different?
Well, I think yes, I do. As maps, they may be talking about power. As calculating instruments that analyze or represent the human relationship to other human beings and to the cosmos, there are another set of tasks that they are capable of performing. And I do think that globes are ways that people can think about their relationship to other human beings and other places, as well as what we are doing in this cosmos.
Oh, yeah.
So I also have a question for you, Tamara. It occurs to me, and please correct me if I'm wrong, that it's a lot easier to draw a celestial globe than a terrestrial globe, because in order to get the data to draw a celestial globe, all I have to do is look up. So my assumption, again, correct me if I'm wrong, is that celestial globes have a much older history than terrestrial globes. And if that is indeed the case, then what I'm wondering is there some geographic area or person who got the idea to start to pair these things up together? Because I thought that was really a fascinating concept of pairing them together.
Right, so they do have an older history, but globes, celestial globes actually do change over time. You can look up, but then when you get telescopes, all bets are off, and you get better and better telescopes, and you start seeing more and more. And at some point, it's like, where do we put all these friggin' stars? We can't fit them on this 18-inch globe. The southern hemisphere, that's something else. They begin to see new constellations. How are we going to represent them? In the 18th century, they actually introduced these constellations. They're going to modernize. Hey, this is the Enlightenment, so instead of these creatures, we're going to have a constellation based on, say, the microscope or the air pump, and they actually have these. But the celestial globe does become problematic. The pairing you find going back into the late Renaissance, and it becomes the model. So it actually, the pairing is set in this older intellectual construct of cosmography, really with these twin branches, and then in some sense gets frozen even as celestial globes become more problematic, terrestrial globes become interesting in other ways, all kinds of, all sorts of things are changing, but the globes in many ways remain frozen because they are coming from this older interest in the cosmos for what it says about individual human experience.
So, but is there a place in time or a place in geography, like, and I don't know, Venice in the 16th century or something, where this pairing starts to happen?
I think, let's see, and I need my Renaissance specialist better. I believe.
No.
Well, but I believe that Mercator himself, who's also a globe maker, that Nuremberg becomes a center of globe making in the early modern period. The English actually don't pick up on globe making quite as much until the 18th century. That's where the Americans are getting their globes. But you have several hundred years of this, and I believe that Nuremberg, then the Netherlands becomes a center for this. So it's been around for a while, that construct.
A really quick add here is if we wanted to put a bunch of dots on the globe, the medieval Islamic world is already pairing terrestrial and celestial globes. There may be some sense of one of those precedes the other, but they largely, in the historical record, come into together. Terrestrial and celestial globes come in together. And it moves from the Islamic world through the German world in the 14th, 15th century, and the Italian world in the 15th century into Northern Europe in the 16th. It's a really long tradition of both of those sets of globes existing, often paired up, and often we see it's a very similar thing to when you see the star map and the sort of star chart and the terrestrial map, circular forms of those, which again date back to the 15th century.
One last question.
Yeah.
Over.
Well, two questions for Penelope, if I may. One of the images you show was a bathymetric chart by Maury, which, if I understood it correctly, used color to show his presumptions about, say, roughly equal depths. And you also pointed out that that chart was based on a bare minimum of bathymetric data. So it raised for me the question, what was their going in hypothesis about the ocean floor and its topography or geography? And how long did it take for that hypothesis to change?
Yeah, so there had been earlier hypotheses about the bottom of the ocean, of course, but Maury pretty much envisioned it as a basin, a flat plain. But that fairly quickly began to change. There began to be recognition of that it wasn't flat, and very quickly he reformulated it as containing mountains and plateaus and things like that. So he doesn't necessarily get the sort of modern concept of the mid-Atlantic ridge and this kind of detail, but he recognizes that there are very different depths and that there are mountain ranges and things. And earlier when I talked about the transatlantic cable, for instance, he actually gets contacted by the people planning a transatlantic cable, and they say, well, what conditions should we be planning for? Is this even feasible? And he tells them that there's a plateau right across the best place to put this between Ireland and Nova Scotia, as if put there just for the purpose of holding a cable. But it's envisioning it as a geography much like a terrestrial geography with the same sort of mountain ranges and features like that.
Random APS fun fact is that Maury was an elected member of the APS and is one of only two whose membership was ever revoked for his service in the Confederacy.
He had his portrait in one of the big merchant halls up in, I want to say in Massachusetts, because he had been such a friend to the merchant with all these routes. And when the war started, they turned his portrait around facing the wall.
All right. I think we're all done. Another round of applause for our presenters.